Good day, everyone. Welcome to today's lesson. We're going to start topic 6 today on curve sketching. This involves looking at the various techniques we've learned in all the units so far in this course and being able to draw an accurate graph given a function. Today we're going to be covering, let me get my drawing tool, we're going to be covering x and y intercepts, vertical asymptotes, which we saw in the last unit. Horizontal asymptotes is something new. And domain and range, we've looked at that before as well. We're not going to be concentrating too much on domain and range in this unit as we've done it before. But again, it's important to be able to look at a function and determine what the domain and the range is. Critical points, that's going to be not in today's lesson, but it's going to be done before long. That involves using calculus to find maximums and minimum points and something called critical values, points of inflection. Concavity, where does the graph concave up? Where is it concave down? You're going to learn a technique for finding that. And then putting everything together, we're going to be making accurate sketches of a graph. So you'll notice now that here on page 2, they've given you a function and they've shown you the graph. I'm just going to quickly point out some of the things in this graph that you will be seeing again. For example, this graph has one y-intercept. Oops, that's not what I wanted. One y-intercept. It also has one x-intercept right here. If it had more than one y-intercept, it wouldn't be a function. Here is your vertical asymptote. And you can see why x equals 3 is a vertical asymptote, because x is not allowed to equal 3. That's a discontinuity, and it's non-removable. Here is a horizontal asymptote. And you'll notice that a horizontal asymptote, if you look at the values of x, as x gets bigger and bigger and bigger and bigger, it gets closer and closer to that line, but it never ever reaches that line. The horizontal asymptote in this case is the line y equals 2. And that's pretty much it. This graph has no relative maximums and relative minimums. I don't know, there are no points of inflection on this graph, which you don't know what they are yet anyway. But all of those things will be coming in the next little while. So let's jump right into how do we calculate the x and y intercepts. You've done this before, and this is true what you're going to see here now, even if it's something as simple as a straight line. The x-intercepts occur where y is equal to 0, so you set y equal to 0. Y-intercepts occur where x is equal to 0, so you would set x equal to 0 to calculate your y-intercepts. And like I say, you were doing that previously even for something as simple as a straight line. So the calculation is actually relatively straightforward. Here's calculation number 1. Let's suppose you want to get the y-intercept first. Well, what you do is you basically set your x equal to 0. And if it's in an explicit form like this one, that's pretty straightforward. So you're going to have y is equal to 0 to the power of 3 plus, or minus, 0 to the power of 2, and then minus 6 times 0, and hopefully you don't require a calculator for that because you're going to get y equals 0. And remember now, if it's a y-intercept, you know the x-coordinate is 0 anyway. So 0, comma 0, there's your y-intercept. Now remember, 0, 0 is the origin. So technically, that's not just a y-intercept, that's also going to be an x-intercept, right? That's going to come about anyway when we look at our next calculation. So to get the x-intercepts, what you do is you set the y equal to 0. Now when you do that here, here's your y, you set that equal to 0, you're going to end up with a cubic polynomial equation to solve. And you haven't solved a whole lot of cubic polynomial equations in any math course. And the only reason you're going to be able to solve this one is because it turns out that x is a common factor. So you remove your x and you're going to have x squared minus x minus 6 left in the brackets. This piece right here, by the way, that tells you one of the solutions of this equation. X is by itself, it's one of the factors. So that tells you that x equals 0 is going to be a solution, meaning it's going to be one of your x-intercepts, which shouldn't be surprising because that's what we just said over there. Now, this other piece is a trinomial, and we'll try to factor that. Hopefully it factors, but if it doesn't factor, then you're going to have to use the quadratic formula and get your x-intercepts approximately as decimals, I would say. So there's going to be x plus 2 and x minus 3 is your factoring. So the x plus 2 That tells you that x equals -2 because x plus 2 could be 0. X minus 3 could equal 0. So x would equal +3. So 1, 2, 3. 2, 3. There's your 3x intercepts. So you're going to have 0, 0. Remember now, it's not necessary to calculate the y coordinate either because they're x-intercepts. The y coordinate is going to be 0 anyway. And this part here is 3, 0. So there's your x-intercepts and your y-intercepts. And as I said, finding those is probably one of the first steps you're going to be doing for all of the functions that you're going to be graphing, locating those intercepts. That's very important. On the next page, 4, vertical asymptotes. And remember now, vertical asymptotes occur when you have a discontinuity in a function. So you look at your denominator, you find out what values you're not allowed to use for x. That's also your domain, by the way. And here, for example, you can see that you're not allowed to use x equals -3 because that would give you a value of 0 on the bottom. The question becomes, is this a removable discontinuity or is it not a removable discontinuity? So what we were doing in unit number 5 is we were factoring the numerator. And in this case, I think you're going to get x and x, plus and minus, numbers that multiply to give you 12. How about -4 plus 3 over x plus 3? And now you can clearly see that even though x plus 3, or x equals -3, sorry, is a discontinuity, it's a removable discontinuity, meaning it will cancel on the top and the bottom. So this is not a vertical asymptote. In fact, if you look carefully at your graph right here, there's the hole in your graph. There's your hole. So now if you just plugged in equals x, the limit as x goes to -3 here, remember, you're actually going to just get -7, which, look, if you look carefully there, that's your y value. So the conclusion that you can make for this question, no vertical asymptotes. I had a student in another class tell me that my handwriting was terrible, which I kind of agree with using this pen. I can't seem to get a good pen. So anyway, that would be the answer for that one there, no vertical asymptote. But there is a hole in the graph. Now the one down below that is different, because if you look carefully at this one, then what you see here is that you know that x is not allowed to equal 2. So that's definitely a discontinuity. But is it removable? And the answer is no, it's not, because the numerator is just a simple 1 that'll never cancel with x minus 2. So, I mean, it's non-removable, which very clearly shows that there is a vertical asymptote at that discontinuity. So a vertical asymptote at x equals 2. That's your domain there, by the way, as well. X is not allowed to equal 2. So that's how you can tell where the vertical asymptotes are located if they exist at all. Look for removable and non-removable discontinuities. Non-removable will give you your asymptote. Okay, horizontal asymptotes. What we do there is we find the limit as x gets bigger and bigger and bigger and bigger, which means it's going to infinity. It's not really necessary to look at it going to positive and negative infinity. Just going to infinity would be good enough. And because if it's going to infinity and negative infinity, if there is a horizontal asymptote, it'll go to that asymptote in both directions. So what we do is we take the limit as x approaches infinity of 1 over x minus 2 squared. And of course what we do there is you just try to plug it in. Remember, you just use direct substitution. You see what happens. If you get anything that's reasonable, that you know the result, well, that's your limit. That's exactly what happens. So if you just plug infinity in there for x, you're going to get infinity minus 2, well, that's still infinity. Infinity squared, by golly, that's infinity as well. Now, you've seen this. You saw this back in chapter number 5, in unit number 5. 1 over, or any number, over an incredibly large number, well, people, that's going to 0. So there is a limit here. The limit is 0. And so in that case, you know that there is a horizontal asymptote at, yeah, my handwriting is terrible, all right. Horizontal asymptote at, and now because it's horizontal, it's y equals this time, y equals 0. So if you were drawing the graph of this function, noting that and actually putting it in would be an important part of that graph. And let me see, what else do we have here? The only other thing here is domain and range. And like I said, we're not going to concentrate a lot on domain and range. If you're drawing the graph, it won't be necessary to give the domain and range. We were looking at this back in the unit that we did on functions. To get your domain, remember, you just basically look at the x's that are there, and you ask yourself, well, what am I not allowed to use? What am I not allowed to use for x? Well, if you look in under here carefully, under that square root sign, you have x plus 3. And what you were doing, what we were saying is, remember that piece that's under the square root sign, it has to be greater than or equal to 0. Otherwise, you're going to get an imaginary solution. Well, just bring your 3 over. So x must be greater than or equal to negative 3. Now, that's how easy it was to get the domain in this case. So your domain, here, I kind of wonder if I use my finger. Values of x such that x is greater than or equal to negative 3. X belongs to the real numbers. But as I said, I won't be asking you for a domain and range when you're drawing the graph. And for the range, well, the range means your y values. So remember when we did square root functions, the range was the values you're going to get back is going to be greater than or equal to 0. But you're subtracting 4 from that. So it can go all the way down to negative 4. And that would be your range. If you plugged it into your, say, a graphing calculator and looked at it that way as well, that would also be one way to determine what your range is. So values of y such that y is going to be greater than or equal to negative 4. Y belongs to the real numbers. Some of you are also giving domain and ranges using interval notation instead of set notation, and that would be fine as well if you know how to do that. So what I'm going to do now, this finishes up today's lesson. We've looked at x and y intercepts. We've looked at vertical asymptotes, horizontal asymptotes, and domain and range of the function. So what I'm going to leave off with today, I'll finish there, and I'd like you to note that on the next 2 pages, 6 and 7, there are some practice questions. 1, 2, 3, 4, 5. Oh, we only have 5. So what I'd like you to do is attempt those questions. Go and look at those questions. Remember now, the detailed solutions are posted up on D2L anyway. You can look at those, but please give them a try yourself first. Does this function blah have any vertical asymptotes? Well, I mean, just by looking at it, I can see, yeah, there probably are. There probably are. So let me see, what would you do there? Now, this time the numerator doesn't factor, but by going to the denominator does. So if you were to factor that denominator, here's what you would get. You'd have an x on the top, and now on the denominator, here's a common factor of x in front of x minus 1. Now, there's 2 discontinuities, 2 of them. X equals 0 is a discontinuity. But also, if you look at the piece in the brackets, x minus 1, well, x is not allowed to equal 1, so x equals 1 is a discontinuity. So what are they? What are they? Well, which one is factorable? Or sorry, which one is canceling? Which one can you remove? Which one is removable is what I meant to say. Well, the x is removable, right there and right there. So that's not a vertical asymptote. In fact, x equals 0 is going to be a hole in the graph. But the x minus 1 is not removable, so that's going to be your vertical asymptote right there. So there you go. Question number 1 done for you already. So I'll stop there. You try the remaining questions, numbers 2 to 5, and keep checking the solutions, keep checking the answers. And tomorrow we're going to be starting on page 8. I believe it is. Page 8, and this is called critical points and critical values, and that's where your knowledge of calculus will come into play there. Okay, so I'll stop there. Have yourselves a wonderful evening, and I'll see you again tomorrow in our next lesson. Bye-bye. Oops, I need my mouse. Bye-bye again.